All right, guys, so before we get started, are there any questions for the assignment so far? Now, what we're looking at first is addition and subtraction, adding or subtracting these rational expressions. Now, looking at the first one here, whenever we have two radicals with the same root, so here both fourth roots, and the same number inside, we can add or subtract them from each other. Add or subtract them together. So if we look at this first one here, we have the fourth root of 10 plus 7 times the fourth root of 10. Now, since we have both of them with the fourth root of 10, we can add the two together. Well, how many fourth roots of 10 do we have in the first one? So how many fourth roots of 10 do we have here? We got one of them. How many do we have here? So total we have. And that's it. That's all we've got to do with these here. So if the roots and the indexes, or the index root, are the same and the number inside them is the same, we can add them together. Since we have one fourth root of 10, and we add to it 7 fourth roots of 10, we have a total of 8. Now, if we look at the other one here, now we can do the exact same thing with fractional exponents. Bless you. So if the bases are the same, and the fractional exponents are the same, we can add them together. So here we have 2, and we add 10 to it, so we have a total of 12. And that's it. Now, another way we can look at both of these here is with factoring, because if I factor the fourth root of 10 out of both, so we have the fourth root of 10, parentheses. If I factor fourth root of 10 away from the fourth root of 10, I'm left with 1. Plus, if I factor the fourth root of 10 out of 7 times the fourth root of 10, we're left with 7. Well, 1 plus 7 is 8, and 8 times the fourth root of 10 is 8 fourth roots of 10. 8 times fourth root of 10. Same thing's true with this here. I can factor the 8 to the 1/5 away from both of these here, which leaves us with 2 plus 10, which 8 to the 1/5. 2 plus 10 is 12, so we just get 12 times 8 to the 1/5. And we can just add the 8, or the 2 and 10, and get 12. Questions on these first two here? Now the next one. Again, the root and what's inside have to be the same. Well, is 54 and 2 the same? No, but the roots are, because they're both cubed roots. So what we need to see is, can I rewrite the cubed root of 54 as a number times the cubed root of 2? Now we can factor this down. So one of the factors of 54 is 2. It would be 2 times 7. Yeah, we pick a prime number. So 2, 3, 5, 7, 9, but not 9. 2, 3, 5, 7, 11, 13, these prime numbers. So I always start with a small one. So I know 54 is divisible by 2. And it's going to be 2 times 27. Then we see a prime factor for 27 is, and 9 is. So we want these prime numbers. So here 54 is third times 2. So the prime factorization, so that we can take cubed roots, we can see multiples of these primes that in a cubed root would reduce. So really what we have is the cubed root of 3 to the third times 2 minus the cubed root of 2. Now we can reduce this here. So if we wanted to rewrite the first one, we could say we have the cubed root of 3 to the third times the cubed root of 2 minus the cubed root of 2. Well, the cubed root of 3 to the third is Cubed root of 3 to the third would be 3, because our third and third root simplified. But it'd still be multiplied by the third root of 2. And we're still subtracting from it the third root of 2. Now do both terms have a cubed root of 2? So we can subtract them. So 3 times the cubed root of 2 minus the cubed root of 2 would be the cubed root of 2. 2 cubed roots of 2. And that's it. Cubed root of 54 minus the cubed root of 2 is, now if we did 2 times the cubed root of 2, we do get the exact same number. So we can't plug them in and get it in simplest radical form, but we can check it with the decimal to make sure they are the same. So 2 cubed roots of 2 is the correct answer, but the calculator won't give us that exact answer. It'll give us the decimal approximation of it, and we can use that to check the answer, but it won't give us the exact answer we need. Questions on any of this here? All right, let's look at 3 more of these. Now the first one, I think, is not too bad.
So then will we just add a 1 plus 7?
Yes.
Five.
5 roots of 12. Now we don't have to take it any further than this here, mainly because we can't actually simplify the 5th root of 12. That is as simplified as it gets. So this is the final answer. 9 to the 2/3 is not, we can't simplify it in any way. I mean, we could rewrite it as 3 to the 4/3 because 9 is 3 squared. 2 times our 2/3 would give us 4/3, but that really doesn't simplify anything. So here, because we can do the 4 plus 8, since our 9 to the 2/3 is the same in both, we can add the numbers in front. Number 12. So if they're not the same, we need to try to make them be the same. So the cubed root of 5 is fine. We need to rewrite the cubed root of 40 or simplify the cubed root of 40 so that we have a number times the cubed root of 5. Yes? So what we're really trying to find is the perfect cubed factor of 40. Number times itself 3 times. So we can factor 5 because we know we need 5 as one of the factors, yes? And what times 5 is 40?
8.
Is 8 a perfect cube?
Yes.
Because what is the cubed root of 8? Yeah. Well, we could do that in a calculator. We can say the cubed root of 8 is, so we're really taking what? Plus 2 times the cubed root of. And that's essentially what we did on the last one. Because if we can look back here, so we know we'll need 2 to match up. So the other is, so I can take the cubed root of 27, which is, and plug it in. Now we just need to finish this up. Yeah. 3 cubed roots of 5. Yeah, and really what we're saying is that this here is not actually in simplest form. The cubed root of 40 is not simplified. It's actually 2 times the cubed root of 5. Because it had a perfect cube in it that could be reduced. Then we can actually combine like terms. Questions on any of this here? Now, those aren't that bad, so we're not going to do a ton of them. We'll do those there, and I think we kind of get the concept. This next part is whenever we apply these odd and even roots to odd and even powers, there is something that occurs, because if we take the even root with an even power, we have to put an absolute value around that variable if the exponent's odd. Now, I'm not going to specifically, especially on the homework, count all points for this if you don't include it or do. If you do include it, awesome. If you don't, I'm not going to count points off because it is a little, not finicky, but there's only specific times we need it. And I'm going to write out the example that they gave us here. So if we take the fourth root of 3 to the fourth power. Now we're very used to just canceling this out and saying that the fourth root and fourth power will simplify. Now if we actually do this, 3 to the fourth, so I can take a calculator and say 3 to the fourth is 81. And if we take the fourth root of it, well, the fourth root of 81 is 3. Okay. So if we said x was 3, and we applied that to our fourth root of x to the fourth, we get 3. Okay? Now this time, we're going to say x is negative 3. So in this here, we'd have the fourth root of negative 3 to the fourth. Well, in the calculator, we can take negative 3 to the fourth power, and we get positive 81. So we're taking the fourth root of positive 81, which we already found out is 3. So the fourth root of x to the fourth is x. Yeah, we can say if we plug 3 in to the fourth root into this, we do get positive 3 back out, yes? But if I plug negative 3 in, do I get negative 3 back out? No, we get positive. So that's why it's saying that if we take the fourth root of x to the fourth, we get the absolute value of x. So we have to make it positive. We have to take that into account. Questions on this here? Now, I'm going to erase this here. Now, if we said the eighth, what we get, so I'm going to change this here just a little bit. Eighth. Now, it's not going to be 81 anymore, and that's not going to be 3. Not 81. So 3 to the 8th. 3 to the 8th power. Yeah, 65, 61. And if I take the fourth root of it, 65, 61, we get 9. So we plugged in 9, or plugged in 3 and got 9. Well, 9 is just what? 3 squared, yes? Now, if we did it here and kind of worked it out, fractional exponents, 8, because this again, it's coming from the nth root of a to the x, is equal to a to the x over n, and we'll use this again in class later on. It's saying that we have 8 over 4, yes? Because the exponent, x to the 8th, the 8 goes on top, and our root is 4, so the 4 goes on bottom, yes? Well, 8 over 4 is what? 2. So the fourth root of x to the 8 is x squared. And we see that because when x is positive 3, we get positive 9, yes? Now, if I take negative 3 to the 8, we'll still get 6,561, and it'll be positive. And the fourth root of it is still 9, yes? What is negative 3 squared? Well, negative 3 squared is positive 9, yes? In this case, we don't need the absolute values because x squared takes care of the negative. So do we see that?
Yeah, let's just fix the math and now it's positive.
Because so if we multiply a number by itself, a negative times a negative is a positive. A positive times a positive is still a positive. So in this case, we don't need the absolute values because that even exponent took care of it. So you kind of see. Now, if it works out that we do an even root and an even exponent and somehow get an even number, we don't need it. If we get an odd number, and the really only case is if they match up, then we need the absolute value because of that kind of negative case we saw first. But also because of all that kind of stipulations to it, I'm not counting off if you don't include it. Okay? But again, I want you to guys, we're going to do it here, especially in the notes so that y'all see it. Y'all kind of know how it works. But I'm not going to be critiquing on that because that's very a minute point. So, not that big. This one. Now we don't need the absolute values with odd roots because the odd root doesn't make a big difference. So for the first one here, the cubed root of 64y to the 6th, no matter what happens, we don't need absolute values. Now, the first thing I'm going to apply is our product property so that we can kind of break these up and take the roots individually. And once you get comfortable with these, you really don't necessarily have to do this. We can start manipulating the properties as we look at them. Now, the first thing that I normally do is when I look at, say, the cube root of 64, we can try plugging it into the calculator. Because if the calculator gives us a nice number, a nice natural, an integer, then we know it has an even root, and that's it. If it gives us a decimal, then we're going to go through the process we've done before. Here, the cube root of 64 is 4. So that means I can come back here and say that this is 4. I don't have to do anything else to it. If it had given us a decimal like earlier, like the first few that we did, part C and part 12, then we have to do our factor trees and simplify from there. Now, the cubed root of y to the 6th would be what? It would be indeed. Because we're talking about taking groups of 3 out. How many groups of 3 can we take out of y to the 6th? 2. So we have y squared. And this is, especially with this one here, I'm always back and forth on how to go about it. Because if we see that, we can do that really easily. We could have just gone from the beginning, took the cubed root of 64, said 4. Okay, I can take 2 groups of 3 from y to the 6th and say y squared. The other method is I can rewrite it as a fractional exponent. We put the exponent of 6 on top, the root of 3 on bottom. Well, 6 over 3 is, and we have that there. If there is a fractional or fraction remaining, it goes back in the radical. We have this here. That's it. Now we could see this here and again do that same method. How many can we pull out of the top and bottom of the fraction and write it that way? Now what we could do also is rewrite it in our parts. So on top we have the 4th root of x to the 4th. On bottom we have the 4th root of y to the 8. Now we know that this will simplify nicely if our powers inside the radical are nice multiples of the root, the index. So the index for both of these here is 4. The numerator, 4 exponent, and the denominator's exponent of 8 are nice multiples, so they will simplify nicely. Now what we can do from here is rewrite these as fractional exponents. So for x, we would have 4 from the exponent and 4 from the root. In the denominator, the numerator would be 8, and its denominator would be 4. So again, that's coming from our nth root of a to the x. Nth root of a to the x is equal to a to the x over n. It's how we can switch from radical form to exponential and exponential to radical. We go from one to the other. Now the numerator, I think we could have seen it from the fourth root of x to the fourth, and especially with x to the 4/4, that's just going to simplify to x. Now the denominator, it may not be as easy to see the fourth root of y to the 8th, but we can see it a little bit better, especially as y to the 8 over 4 is going to become y squared, because we can take two groups of 4 out, which leaves us with y squared. Questions on this here? Now this one here is one of the cases where we would need the absolute values with the numerator. Because we went with an even root, even power, we would need it. I will take it as either x over y squared or the absolute value of x over y squared. But that would be one of the cases where we need to adjust for the possibility of a negative in the spot of x. Questions on any of this here? So looking back at this here, do we like the fractional exponents or do we like taking the groups out or seeing both? So we can do that both ways, especially if that doesn't make sense. So when we look at this here, I'll do the kind of groups out first. So the first thing we're looking at is the cubed root of 27. We can grab a calculator and see cubed root of 27 is 3. So in either case, that there is kind of nice. So we can say 3. Now taking the cubed root of 12, we're trying to see how many groups of 3 can we take out? 4. And that's it. Now if we did it the other way, because we could still say the cubed root of 27 is 3. Now for d, as a fractional exponent, we could say, 12 on top, 3 on bottom, which is still going to give us 3d to the 4th. So there are different ways to look at it, but they end up giving us the same result. Is all we're doing with this is saying, okay, 12 over 4, how many groups of 3 can we take out? Now we look at this one here. Again, we're doing the same type process. Now we don't have a number specifically, so we don't necessarily have to plug anything into the calculator for cubed roots. But again, on top and bottom, we're taking out groups of 4. And if we look at the numerator's exponent, which is 4, denominator's exponent, which is 16, will we be able to take an even amount out of both and take everything out? Yeah. On top, we would have 1x, because we can take one group of 4 out of x to the 4th. How many groups of y can we take out of y to the 16th? And then we can include the absolute values if we want, because we took the 4th root of x to the 4th, and we just get x. Questions on this here? Now, this one here is again doing the exact same thing. So we're taking the 5th root. Yes? Now, if we look at, say, 5th root of 4, back up. I'm going to give us a little more space. 5th root. So we're going to do kind of the grouping method, or kind of pulling out method that we did on the last one. Can I take the 5th root of 4? No, because 4 is 2 squared. We would need 3 more 2's. We can't do it. So the 4 is not going to be simplified out of the radical. So we can leave the 4 inside. A to the 8th is our next one. Can I take a group of 5 out of it? We can take 1 out for sure, yes? So I can write this to the side. So we have 8, and I took away 5. So I have 3, yes? Can I take another group of 5 away? So that means I have what? Left inside. Because when we took it away 5 once, that means we have one group that comes out, and we have 3 left over. Because if we think of it as a rational exponent, so a is to the x over n. Well, x in our case is 8, and the n is 5. As a mixed number, that would be 1 and 3/5. We have 1 that comes out, and that 3/5 stays inside. The 3 of the 3/5 is our exponent. The 5 is the root of the radical. So we get it that way there. If we look at B, so 14. Well, I can take 5 out of it once, yes, which takes it from 14 to, can we do it again? I can say 9 minus 5 is, so we get 4. Can I take 5 away again? No. So how many B's come out? 2, because we were able to take 5 away twice. And how many do we have left over? Yeah. So we have B to the 4th left over. And lastly, we have C to the 5th. Right? Because we can take 5 away from it once. So C would come out. Are there any left inside? And that's it. Yeah. Because we can look at it in this one of these two ways. Because we can look at it as fractional exponents. The whole numbers are what comes out. The top of the fraction is what stays inside. Or we can do it this way too. We're going to come back to this problem. I really need to reorganize these notes. Because I want to look at this one next. I want to do another one of these here so we can kind of get the pattern before we jump to the other type. I have a feeling we want to do it the kind of pull out method. So the first thing we look at is, can we take the cubed root of 2? Now 2 is prime, so we can't take the cubed root of it, so it's going to stay inside the radical. A to the 13th. Yeah. Right, we can take it out 4 times. Because we can subtract 3 from 13 4 times. 4 minus 3. So on the outside, we're going to have a to the 4th. Because we can take it out 4 times. We can take 4 groups of 3 out. How many are left inside? 1. Because when we do our kind of subtraction, here we have 1 left over. So it's 4 1/3, and the 1/3 is our cubed root. If we look at b to the 3rd, well, we can do 3 minus 3, which is 0. So we'll be able to take 1 out. How many are left inside? 0. Because the cubed root of b to the 3rd is just b. And the last one, c. Well, we can subtract it once. Get 5. Well, we can subtract it again and get 2. Can we subtract it a 3rd time? No. So how many come out? How many are left inside? 2. And that's it. Questions on any of this here? Be ready for the next type. So we're going to go back to this one here. Now, this one here, we've done something similar to it because we did some of these yesterday where we talked about rewriting the cubed root of 4, or not the cubed root, we had the 4th root of 4 and we rewrote it. So we had 1 over the 4th root of 4, and we rewrote this as 1 over the 4th root of 2 squared, and we're trying to simplify that radical. We're doing the exact same thing here with variables, because we need to multiply the top and bottom of this fraction by something so that the denominator radical will simplify out. So we need to simplify the cubed root of y to the 8th, yes? Now, what would we need to multiply that by to get it to simplify? So we need to multiply the bottom, yes? Well, the only way that we can multiply two radicals is if their indexes are the same. So, okay. So that means the top and bottom of this are going to need a cubed root. We got both of those in green. So those match up, yes? So, well, we know we can't take the cubed root of 8. Because when we're talking about this, we're talking about groups of 3s with variables. So with 8, I can take one group of 3 away just fine, which gives me 5 left over, yes? I can do it again, which leaves me with 2. But I need this to end up being 0, yes? Well, I have 2 left over. How many more do I need to be able to take another group out? 1, because if I have 1, we have 2, yes? If I had 1 more, we would have. So I need to multiply top and bottom of this by 1y, or y to the first, yes? Because if we had this, this would not be true anymore. Because if we do the multiplication, on top, we're just going to have x times the cubed root of y. On bottom, we can multiply what's inside the radicals, because we still have the cubed root, but y to the 8 times y is now y to the 9th, yes? Now if we do this subtraction again, 9 minus 3 is 6. 6 minus 3 is 3. 3 minus 3 is... So the denominator is now what? Y to the 3rd. And that's it. So we're doing this here, we're trying to find the next exponent that we need to increase this y by to be able to get it simplified. So in this case it is 9. We needed 1 more, so we multiplied top and bottom by the cubed root of y to get the denominator to be the cubed root of y to the 9th, which is y to the 3rd. So we're trying to find the next exponent that would simplify. Does that make sense? It's one of those things that is, I think now that we can see it, is there's not a whole lot to it. It's, once we get the concept, yes, it makes sense, but it's complexly simple, if that kind of makes sense. There's not a whole lot to it, but it is complex at the same time. Once we see it, but until we see it, we don't. We're going to come back to this one tomorrow. We're not going to have time for it today. But I do want to look at this one here, because I do believe we can get this one done pretty quickly and finish up here. So with this here, we're going to have to multiply the top and bottom by the cubed root of something. And the reason we use cubed roots is because the denominator is a cubed root, yes? Can we take the cubed root of 13, y to the 13 nicely? No, because 13 is not divisible by 3. What is the next power after 13 that is? Yeah, 15, because 12 was close to it, because 4 times 3 is 12. But since we have to go up, the next number after 12 is 15. So how many are we missing? 2, yes? So we're going to multiply the top and bottom of this by the cubed root of y squared. So the numerator is going to be x squared times the cubed root of y squared over the cubed root of y to the 15th. And what would be the cubed root of y to the 15th? 5. Because we can pull 5 groups of 3 out of 15. So we get y to the 5th. And that's it. Questions on any of this here? And really for this here, those are 2 of the harder parts of this. And we'll finish these note sheets up tomorrow with the rest of this here. Now,